I'm back, and so I wrote up above here what have we learned so far. The definition of what pressure is, force divided by area. Density, rho, is equal to mass divided by volume. And now we've learned what static pressure is. And so static pressure is going to depend on what's the pressure that you begin with, and then you add to it the additional pressure caused by being under the fluid. Now normally the fluid is going to be water, in which case we're going to want to use the density of water here. And then G is going to be the 9.8 meters per second squared, and then H is going to be your depth under that particular fluid. Now we want to talk about fluids that are in motion, and so we're going to talk about volume flow rate. And so the definition of the volume flow rate is it's going to be the amount of fluid that flows in a certain amount of time. And so we're going to say, now I'm going to abbreviate this, and instead of saying volume flow rate, what about if I just said VFR for that? Now in some textbooks they actually would do it this way, and they put a dot over the top of it, but I'm not going to be that precise. So instead of having to write that down like that, so I'm going to say the volume flow rate is VFR, and then it's going to be equal to the volume of water, or whatever the fluid is, in a certain amount of time. Now let's look at the units. So the units for volume are going to be cubic meters. So 1 meter by 1 meter by 1 meter. And then the unit for time is going to be the second. So therefore the units for volume flow rate are going to be cubic meters per second. So here's a sample question. You have 10 cubic meters of water coming out of a pipe in 2 minutes. What's its volume flow rate? So we're going to write down what we're given. So the volume is 10 cubic meters. The time was 2 minutes, but that's not the official metric unit. So the official metric unit is going to be the second. So we'll use 120 seconds. And we're looking for the volume flow rate, the VFR. And so we're going to plug into this formula and then solve it, and it turns out to be 0.083 cubic meters per second. So here are some typical volume flow rates. So this would be, I took a cup and held it underneath the bathroom faucet, and I had a stopwatch so that I was able to time it. And it turns out that for a typical bathroom faucet, it's 0.00011 cubic meters per second. Not very big. And then I looked it up on the internet for the Alaskan pipeline to see how fast is the oil traveling through that pipe. And then also tried it for the Springfield Dam in Springfield, Missouri. When they let the water out of the dam, how fast is the water coming out? And then I looked it up for Niagara Falls, and then I also looked it up for the Mississippi River. So the Mississippi River carries a huge amount of water is traveling in that river per second. Okay, let's continue with this idea of the volume flow rate. So we know that it is a volume divided by time, but we could, instead of saying the volume, we could also say that it's going to be an area and then multiplied by a certain distance r, and then we're still dividing by t, and then notice that these two things can go together. So the distance that something travels in a certain amount of time, that was the velocity. So therefore we could say that this is going to be equal to the velocity of the fluid multiplied by the area through which it's going through. Now, if you have a pipe and there is no additional sources of pressure, so pressure goes into the pipe and then the same pressure comes out of the pipe, that will be true as long as you have a pipe that doesn't have any leaks in it, or you could maybe have a pipe where there's another pipe coming into it, and then that could add additional pressure. So let's just assume that this pipe doesn't have any leaks and it doesn't have any additional pressures. Then we could say that the volume flow rate going into the pipe has to equal the volume flow rate coming out of the pipe. Or we could say that the velocity of the fluid going into the pipe times the area going into the pipe has to be equal to the velocity coming out multiplied by the area coming out. And you could prove this with a garden hose. So if you have a regular garden hose and you turn it on, the fluid is going to be coming out of it. But then if you take your thumb and you put it over the end of the garden hose, what are you doing? You are decreasing the area. And so if you're decreasing the area, then something else must change in order to compensate. So the velocity will increase. If you decrease the area, then the velocity of the water coming out of the hose has got to increase. So here's a sample question. Water flows through a pipe that has a certain cross-sectional area and it has a certain speed. What would happen to the speed of the water if it travels through a pipe that has 1/3 the area? So we're going to decrease the area to 1/3. Well, if something decreases, then something else has to increase in order to compensate. So the speed of the water is going to increase by a factor of 3. Okay, let's take a break. And when we come back, we're going to talk about the pressure associated with a moving fluid.